Welcome back, everyone. We will start with a talk by Piyali Chatterjee. She is a faculty at IIA in Bangalore. She did her PhD from IISc. She previously held postdoctoral positions at Nordita Stockholm, the High Altitude Observatory in Boulder, USA, and the University of Oslo. Her research areas include solar MHD waves, jets, flares, and CMEs, and dynamo theory. She is a member of the Pencil Code Steering Committee since 2020 and the WGGE ASI chairperson since 2025. So, Piyali.
Yeah, thank you, Rajeshwari. So I thank the organizers for creating this very safe and trustworthy place for us to share not just our work, but maybe sometimes I'll intersperse my talk with some personal stories, which I wouldn't do in a normal conference. So yeah, I once again thank you for making me trust this space. So this is a story which is very close to my heart, because in this science, I could involve my family. So basically, this is about connecting something known as solar spicules, which are millions of plasma jets on the surface of the sun, with something that you can do in the lab. Some experiments, some tabletop experiments that you can do in the lab. So before I go into that, I'll give you a little bit of a background about solar spicules. So these are like millions of jets which you see on the solar surface in the chromosphere and transition region of our star. So these are ballistic jets, which basically means that their dynamics is governed by gravity. So if you follow their tips, they will follow parabolic paths, right? They rise and then they fall. And their dynamics is governed by half AT square, essentially, where A is the acceleration of the jet. And these typically have vary lengths, 3,000 to 16,000 kilometers. And they are very pointy, so the aspect ratio is large. And they are like usually of supersonic speeds, varying from 20 to 70 kilometers per second, so which is supersonic on the surface of the sun. And they are seen in various emission and absorption lines depending on where you are looking. And why are they important? The importance comes from the fact that it is believed that since there are so many of them, they must be transporting something to the solar atmosphere. So for example, momentum, mass, and energy. And that may have a contribution to powering the solar wind and also heating the million-degree corona of the sun. Like this is a grand challenge problem, right? That the solar corona is at million-degree, whereas the solar photosphere is only at 6,000 Kelvin. Okay, so now there are a lot of theories that exist, but and there have been a lot of simulations also, but so far the simulations have not quantitatively explained the heights, the speeds, and the fact that there's a forest of jets. Like, why are there so many jets? So that has not been explained. So we decided to look at it from a different point of view. We tried looking at it from this popular science experiment, which you have all maybe seen on the YouTube. So it's just that you take a speaker and you can pour paint on the speaker and turn on the music, and then you will see the paint basically dance like this and produce jets. And they visually look very similar to the solar spicules. Here they have been captured by the Japanese satellite known as Hinode, and they are being observed in the calcium ultraviolet light. So they are also, like, you see these jets going up and falling down. So there's a lot of visual similarity, but does it end there? Or there is more to it? And can we study the system in such a way that to explain the properties of this system, the astrophysical system, can we say something by studying the lab system? Like, can you can you do this experiment in an undergrad lab? And, some students may, be really excited by looking at the lab experiments. Oh, this is what is actually happening on the sun. So to do that, you actually have to show similarities on different levels. So we found that there is a lot of mathematical similarity in the way the viscoelastic stresses in the fluid have parallels to the Maxwell stresses in the MHD, in the magnetohydrodynamics. That is the approximation of that we use to study the solar plasma. So not just that, so there's mathematical similarity and the visual one, but we also have to show that there's phenomenological similarity. Like, is there, like, if you try to build a phase space of different quantities in this particular model, can you also build a similar phase space in a different, in a different system? They're very widely disparate system. Can you show that there are phenomenological similarities? So this is what we tried to do. So this is the backstory of that. So this is an article published, written by Subhashri Deshikan for Hindu. So it says a homemade analogy that helps study solar spicules in the lab. So yeah, it says the spark came from then 8-year-old daughter. She's a teenager now. So she was watching, my daughter, she was watching, these psychedelic videos of paint on the speaker. And by the time the COVID hadn't started, but then she used to see that we are doing this MHD simulations of solar spicules, and there would be all these animations that I would look at on my laptop. So I and my first PhD students, we were already working on this by that time. And one day she commented that these jets are actually looking like your spicules. Huh? So then what happened that, my husband Murthy, so he works at the Azim Premji University, and I told him this. And he's also not from fluids background. He's a condensed matter experimentalist. And he also got excited by the fact that a child who doesn't have any idea of the laws of physics is basically making this connection. So is there, like, should we, delve deeper or not? So he said, let us try to do some experiments. So he started doing some experiments in his lab. So, but then in the meantime, what happened that COVID set in and there was a lockdown. And somehow he predicted that something like that will happen. So he got a lot of stuff home. Just, I think 16th March was probably the start of the lockdown. Just 2 days before that, he got all these speakers and some amount of, things we used to make these fluids home. Because I hadn't seen what he's doing in the university. And so, everything is now at home. So this is a photograph of us doing the experiment at 1 a.m. at night. So we had to do the experiments at night because, so, there's a speaker, so you have to vibrate it at a certain frequency. And we want honest input to output conversion. We don't want noise in the power line, the 50 hertz power line. And during the daytime when everybody is at home, they are all working from home, there is a lot of disturbance. So you cannot use that time. So we had to do all experiments at night. So she was also, this is my daughter, she is probably, cleaning the things that we use to make the polymer solutions. So this is what she's doing. So I'm making a very artificial face, looking at if the polymer has been, made properly or not, and if I'm looking nice on the photo or not. So that's the backstory for this thing. So I'll go back to the science now. So what we started with is, okay, these are two disparate systems, but why should we go and explore the similarity? So then in fluid dynamics or even in MHD, there is something known as scaling. Right. So if you can show that the larger system and the smaller system are related scale wise, then maybe it is some positive thing, right? So this may represent the other system. The smaller system may represent the bigger system. So then we looked at the plasma jets on the sun. So they have this particular length scale in, like 500 to 1,000. Oh, this is not the length scale. This is the width of the jets, 500 to 1,000 kilometers. Their length is like 7,000 to 20,000 kilometers, and the velocity is in kilometers per second. And similarly, for the paint jets, we have these scales, but in centimeters. So then with this, we can create some non-dimensional numbers, right? So when we create some non-dimensional numbers, and if those non-dimensional numbers are comparable to each other, you know that these systems may have some similarity. And that is what we found. For example, just the simple thing, aspect ratio of the jets. So the jets in the laboratory and the spicules on the sun, they have very similar aspect ratio. And there is this other number known as the Froude number, which basically tells you how how the surface distortions are governed by gravity. Something to learn about, say, surface gravity waves in that system. So that number is also very similar. So this is like, you can just see those numbers here. They are very closely related. And then what about the acceleration given to the jet versus the surface gravity? So for the lab, the surface gravity is the Earth's gravity, and we know the forcing we are giving, right? If you can feed a sine wave to a speaker, so you can calculate the acceleration of that, and then you can take the ratio of that acceleration to gravity. Similarly, on the sun, also you can calculate what is the forcing at the base of the spicule, and then you know the surface gravity of the sun, you can take a ratio. And then this last number is basically the dominant frequency of driving into the lifetime of the jets. So that is a non-dimensional number. So this driving frequency for the sun, for the solar convection, is basically the 5-minute mode. You may all heard of the 5-minute mode, right? So which basically, if you convert to frequency, it is 3.3 millihertz. So basically the surface of this sun, if you take the velocity and do a velocity Dopplerograms and you do a Fourier transform, the dominant frequency will be 5 minutes. So we use that frequency. And for the paint jets, we were driving it at 30 hertz, around 30 hertz. So we took that frequency. So that is in millihertz, and this one is in hertz. But then if you multiply it by lifetime of jets, they are again in the very similar range. So far, so good. That's really good. And then we went on to do some literature survey where we find that, people have done these experiments which are known as Faraday excitation. So they take this fluid and then they shake it up, and then a lot of patterns which form. And these patterns become more and more complex as you increase the frequency and amplitude of the driving. So this is an experiment that we did. So again, there's this beaker where we have put a polymeric fluid. And then the music is basically the actual P modes, the solar P modes obtained from observations. We just speeded it up, and then we fed it to the speaker, and then we saw that there are these jets that are being produced. And yeah, so why are these jets being produced? So that also in the fluid context, people have studied that what happens is the surface is undergoing all these changes. And during that, sometimes the surface will form cusps like this. And when you have cusps like that, the surface will want to not have discontinuity in the slope. And therefore, they will want to go back to a smoother slope. And the process of going back from the surface singularity to a smoother surface causes this formation of jets in the fluid case. Now, what happens in the sun? In the sun, we have trapped P modes because the sun is a cavity. There are these P modes, and the study of these modes is known as helioseismology. But then what happens that again, the surface of the sun is not a rigid body because it's made of plasma. So it's a leaky channel. It's not as leaky as we were discussing about the leaky channel, but still there are a lot of modes that leak out if the frequency is greater than a cutoff frequency. And these modes, they escape into the atmosphere. And there are relatively stronger magnetic fields. And these sound waves, they become what are known as magnetoacoustic waves. And this is basically a simulation that has been done by my student. So you see the convection happening in a solar-like model. So this convection basically is giving rise to this 5-minute mode that is happening. So in the fluid, the jets are being formed because of this discontinuity, whereas here you have these high frequency P modes that are escaping and interacting with magnetic structures here. And as you know, that as a wave propagates from a denser medium to a rarer medium, it becomes more and more nonlinear, right? So if you start with a sinusoidal wave, it will become like sawtooth, like a sawtooth wave. So this is basically known as nonlinear steepening or shock formation, right? So now in the fluid as well as in the case of the sun, that is what is happening, at least in the case of the sun. In case of the fluid, it was surface gravity waves essentially, but there also the waves are becoming nonlinear because of a singularity, and here the waves are becoming nonlinear because there is stratification in the atmosphere. So we do start with this MHD model where we solve the equations of MHD under some certain conditions. And I won't go through this so much. And then we decide to do parallel experiments in both systems. So what we do is we say, okay, we will look at the phase space where we vary the frequency of the driving, both in the lab and in the MHD simulation. And we will look at the minimum driving force that is required to produce these jets in both systems. So this is the question we ask. What minimum value of the amplitude for a given frequency do we obtain a forest of jets? So we do these, this should run, right? Yeah, so then we do these experiments for 3 different simulations here, where the driving, we provide a sinusoidal driving like this. We vary the amplitude of the driving at a particular frequency. And when we vary the amplitude of the driving, there's a driving at which we will see lot of jets, which are above a certain threshold in height. So we say, what is a forest of jets? The forest of jets is defined under certain criteria. So that is up to us. So we say, okay, we need to have at least 4 jets in 10 cycles, and the aspect ratio of the jet should be half, which means the height should be at least double that of the width. So depending the subject to this condition, we can define our threshold. Now we do the same experiment in the fluid. So we oscillate the speaker at different frequencies, and then we can see, we can measure how many jets as we have defined it form, and then we can find the threshold. So doing this, we can create a phase space, acceleration versus frequency in both systems. Now, after doing this, we find that the behavior is actually very similar. So one of the reasons why we are forming jets in both systems is actually an amplitude of sufficient, forcing of sufficient amplitude that is quasi-periodic or periodic. So large amplitude quasi-periodic excitation is one of the requirements in this case. So is that enough? So we did some simulation where I artificially switched off the magnetic field. So when I artificially switched off the magnetic field, there are no jets which are forming, right? They're all becoming some homogeneous mass here. However, when there is magnetic field, for example, let me go back in this movie, you see the jets are more coherent because they are following the magnetic field lines. So what is exactly happening is, as you increase the magnetic field strength, you are going from a more isotropic to an anisotropic situation. So jets are totally anisotropic. So here in this case where the magnetic field was 0, the Kelvin-Helmholtz instability is actually breaking up the jets. Now what about the fluid? So this is a natural example of Faraday excitation, where this crocodile is actually singing a mating song. So basically it is singing at a frequency of 20 hertz or something, and it is producing a lot of jets. But these jets are all breaking. And these are breaking because of what is known as plateau-Rayleigh instability, which is again which was found a long time ago. I mean, these papers are actually from late 1800s. And this is breaking because the water has very strong surface tension. Now, one way of suppressing surface tension is to add polymers in the fluid. So they make the fluid non-Newtonian. So when we study this Navier-Stokes equation and things like that, so we say it's Newtonian. So it's like nu del square V. That is a Newtonian term. But our stress is not always proportional to strain. It can be, stress can be non-linearly proportional to the strain. So there's some non-Newtonian behavior happening here. And when you add polymers, you see the jets become more glassy. So this has been known for a long time, and there is a whole lot of literature surrounding it. And then we showed also that in both systems, the way to introduce anisotropic stress is to add polymers to the fluid on one hand, and on the other hand, in the plasma, in the MHD case, you can just increase your magnetic field from 0 to some threshold value. If you do that, you will suppress the Kelvin-Helmholtz instability in one model, and in the other model, you will suppress the plateau relay instability. And then we can again do an experiment. So we built up these experiments. These are all experiments. All these dots here, these symbols here are experiments. So we actually perform a lot of experiments. And you can show that as you increase the anisotropy, you get anisotropic driver, you get more and more, the system starts looking more and more anisotropic actually. So then from this, we said that, okay, so these are the sufficient condition for the formation of a forest of jets. So you need a fluid medium, and you of course need gravity or stratification, and you need large amplitude quasi-periodic excitation, and you need anisotropy of stresses. If you have these 4 minimum ingredients, it is sufficient to produce a forest of jets. That is a vanilla model for the forest of spicules. And you can have special kind of spicules. You can have some magnetic reconnection, you can have extra jets, or some other esoteric mechanism also. But you just want a simple forest of jets. This is the recipe for producing the simple forest of jets. Now I'll just take a little bit of time here. So again, I go back to my personal experiences. So this, while we did this work, it was all a lot of fun and we enjoyed it. But I realized that by the time the COVID started, that I am from IIA, right? I love IIA, huh? So I mean, if I'm given another opportunity, I will again choose IIA as my workplace. But then I realized that, every time they're asking me for my papers, but I'm not getting the promotion. So what is happening? So then I looked up, there were other people who joined along with me. So I'll call this a cohort of like maybe four people who joined with me and after me. And then I noticed that they were all men. And I noticed that they got their promotions on time, but every year they're asking me for my papers, but nothing is happening. So what's going on? So then I started comparing. I, of course, was not brave enough to go and ask them what you are doing that I am not doing. So I started looking up their CVs and what they're doing, what conferences, the annual reports they are submitting, and then I did not find any significant difference between what they have done and what I have done. Still nothing is happening. Nobody is giving me a clear answer. Then we published this paper in Nature Physics. So I invite you to actually go and read this paper. It is written in a way which is accessible to everybody. So it's only after I published a paper in a Nature brand journal, I was given a promotion. So I like to joke about this, that to get a promotion, if you're a woman, you have to produce a paper in a Nature brand journal. And even then I was told that there were some men in the committee who asked the question that how many papers in Nature does she have? And why are there so many authors on that paper? I'm the corresponding author of this paper. I'm the PI. And I mean, they're not asking me directly, but it's one of, so because in the committee, it's like everybody has to agree to take the case forward. Otherwise, if somebody doesn't agree, then the case doesn't go forward. So this is basically a joke that happened, but I'm happy to say that, things have changed after that, hopefully for the better. And one more thing that I also wanted to say about allies. So I was talking with Manoj that other day, and I said, I really appreciate that you are here because it's not easy for allies also. So again, I will go back to a personal story. So then, so we had a small baby, and at that time, it was time for me to go for postdocs outside India. And then my husband was generous enough to say that, okay, you decide, and then, I will follow wherever you go. But as a result, it's also not easy to get, because he's from a totally different area, it was not easy to get postdocs always. And then his CV has some breaks. And because of that break, when he was applying for, when he would go and talk to people for postdoc, they would say, oh, you have a break here. Why is that break? So I was taking care of my daughter. You are taking care of your daughter, your wife was not there? And this was actually not in India. This was outside India. So then you see, it's also not easy for allies. Because you choose to be an ally, you are subjected to the patriarchy. That why do you have? So it's very difficult for men who are helping out women to explain their career breaks because of the family. It's more difficult than us. Right? For us, it is normalized. But for them who try to be an ally, this is a challenge that they're facing. So I'm sorry if these personal stories are not what I should have shared, but yeah, I mean, there I go. I felt safe enough to share it thanks to the organizers. So yeah, thank you.
Yeah, thank you, Piyali, for the very nice talk and sharing your experiences. Questions for Piyali?
Yeah, I think.
Thank you for the very nice talk. So the connection between the lab experiment and the solar corona jets were really nice. But one thing that I wanted to ask is that the morphology of the spicules that are forming in the lab experiment, are that also similar to that what we observe in the solar experiments? Because when we are vibrating the fluids, so the fluid rises and there's a droplet kind of structure forming at the top of the spicule and then it falls. Do we observe the same thing in solar jets also?
No, that is what. So the droplet formation is because of the surface tension of water, for example. But if I add some polymer to that fluid, then what will happen is, so the polymers are like springs. So what they will do is they will expand and they will absorb that turbulent energy. So then what will happen? The jet does not have enough energy to form that droplet. So then it will be like a coherent jet all over. So it is same as in case of a sun. So in the sun also we have magnetic fields. You have never seen sun without magnetic fields. So these spicules are always along the magnetic field. So if the magnetic field is slanted from the surface, then the spicules are also slanted. So it basically follows the direction of and the aspect ratio, yes, I showed you the table earlier, right? Where we compare the aspect ratio and the lifetime frequency of this. They are very close to each other. See, the physics is very different in both the system. The math is similar, right? So maybe we could actually use these lab jets to study more about the spicules. So that is what we learned from this.
And another question I had an addition. So you were making this analogy between the Maxwellian stress and the Kelvin stress. In terms of the anisotropy, you said to add the anisotropy in the fluid medium, we had to add the polymer. And in the case of the solar jets, we had these magnetic fields which are introducing the anisotropy. So, as you said, that for solar corona surface, the jets are usually directed along the magnetic field orientation. So, can we also make some analogy like what intrinsic factor is the addition of the polymers changing so that the anisotropy and that is correlated or something like that?
So, what is happening is so these polymers are stretching along the direction of the flow, right? So when they stretch along the direction of the flow, they basically are preventing the flow in the perpendicular direction because of the viscoelastic stresses. So I didn't show that slide, but if you look at the stress expression, they're exactly the same. So basically it will prevent any motion in the direction perpendicular to the stretching direction of the polymer. Same as what is happening in the Maxwell, the magnetic tension, B dot grad B. You have the same term in the viscoelastic stress.
Thank you.
Okay, I think one quick question and then.
Yeah, I'm always so amazed by this thing that you have done, this particular work. Yeah, one question I had is like this height of the spicules. I was just wondering, like are magnetic fields, do we have mean magnetic fields correlated on that scale that compared to your simulation magnetic field strength, or how much do you have to worry about the random magnetic fields?
Okay. So actually in the real sun, these magnetic fields are predominantly vertical along supergranular cells. Now our simulations are on a smaller size. So what we did was we imposed a vertical magnetic field, which is everywhere. So our spicules are like, it's wherever the magnetic field is vertical, there are these spicules which are forming. And we can tune that value in the simulation. But what people have found from observations, and there is another paper that has come out since this work, where we see that if you increase the magnetic field, or you look at, say, plage regions versus coronal hole regions, you will see that the spicule height decreases when the magnetic field is stronger. So a stronger magnetic field is actually, it's not letting it go so far. So that also we sort of observe in the polymer fluid, like if you increase the concentration, it becomes harder for like the pulling thing, right? So it becomes harder for the jet to go really high. So that is something we have seen from observations. There are papers which hint this. But obviously you cannot have the sun where we can exactly match this. Thank you.